Back to our talk on Venus, mysteries beneath the clouds. So let's start on the surface of Venus and work our way up. The surface of Earth's land masses are generally made of granite, which requires water in its formation. We find that the current surface of Venus is basalt, which is formed in a waterless environment. This has huge implications for the geologic history of Venus. If Venus did have water, it did so perhaps billions of years ago, and then the water must have escaped from the planet. This mechanism is complex, and we'll touch on it a little bit later. On a practical matter, we simply can't see the surface of Venus, not just because of the thick clouds, but the characteristics of the clouds and the gases absorb virtually all visible and infrared light. There's a few narrow windows in the infrared spectrum that we can see through, and these were only recently discovered in the last few decades. And while they provide only a limited view of the planet, right now they're about the only means we have for a direct view of the surface. Note that when we say we have a view of the surface, this is in the infrared, not in any of the visual wavelengths. The primary means for heat leaving the core of a planet is through volcanoes, which is also the source of carbon dioxide. Of course, this is only an artist's conception. Now, the atmosphere is so opaque that there isn't any means to take the pictures directly. We've been able to identify about 37 large active volcanoes on Venus and perhaps tens of thousands smaller ones. From observations of the planet using special filters, we can see what appear to be plumes reaching up into the upper atmosphere, and these correspond to where we think active volcanoes exist. Additionally, studies also showed that the plumes were rich in sulfur dioxide, which is expected as one of the primary volcanic gases. One interesting thing to note about this image: when we think of volcanoes on Earth, we visualize a tall, cone-shaped mountain with lava running down its sides. This is not what we would see on Venus, because the lava there is very fluid, unlike the thick lavas on Earth that we're more familiar with. We'll be talking about this oddity in a little bit. Most of the volcanoes on Earth form along the boundaries between the tectonic plates, whereas on Venus, there appear to be no well-defined breaks in the surface, and so volcanoes appear wherever there's just a weakness in the crust. A major unknown is the amount of activity of the volcanoes. Are they constantly erupting, or do they lie dormant for long periods of time before coming to life again? To be honest, we really don't know. Now, a bit of geology is important at this point. We have mentioned that the main types of rocks that are created from deep within the Earth are basalt and granite. Basalts are formed by the magma that originates deep below the surface. It's poor in silica, it's rather fluid, and is very, very dense. Most of the Earth's crust that's under the oceans is basalt. Granites are formed very differently. They're rich in silica and are rather viscous compared to basalt, and is very much less dense. This allows granite to float on an ocean of magma, creating the continents. A key part of this formation story is that granite forms when the rock is cooled very slowly, and is such as the case when molten rock is exposed to water. This is an important point. Without water, there would be no granite. And with no granite, there's likely not going to be any continents as we understand them. We also see that on both the moon and Mars, basalts are everywhere and granite's nowhere to be seen. Of course, water has long, since left those worlds as well. What we do see is a result of volcanoes releasing magma, which forms the basaltic crust we do see. Because this type of magma is very fluid, we don't see the tall volcanoes that are common on Earth. Rather, the lava flows in long distances outwards, making these pancake-type formations we see here. But how can we tell if there's any active volcanoes on Venus? Yes, we do see what appear to be plumes high in the atmosphere, and they do appear to originate from areas where we think active volcanoes are suspected. Still, far more comprehensive evidence is needed. Using those narrow infrared windows that are available for us to see through the atmosphere, we're able to make a very low resolution temperature map of the surface and match it to the topography of the radar images created by the Magellan spacecraft. Looking at Indian Mons, I think that's how you pronounce it, it's in the southern hemisphere of Venus, and we can see the upper image in the from Magellan that appears to be relatively fresh lava flows. But peering through the infrared window, we see heat being radiated by the volcano, showing that it's still quite hot and very possibly erupting. Again, we can't see the gas plumes in these wavelengths, but this is pretty conclusive evidence. Now, right now, sitting in your seat on Earth, you think that you're stationary. Now, aside from the idea that Earth is spinning, another action is occurring. The landmass under your feet is in constant motion, and as the several continental plates on Earth move apart or smash together. In geologic time frames, this is quite fast. North and South America are moving away from Europe and the African continent at about the speed that your fingernails grow. If we could roll this process back a few 100 million years, we would find that the Earth would have an arrangement of continents that would be unrecognizable to folks today. This drifting is the result of Earth trying to get rid of the heat that exists in the core of our Earth, with the upwelling of magma pushing these floating granite plates all around. This movement results in earthquakes and volcanoes which release the energy and heat from below. While this is all very, very interesting and it's good to know about Earth, what the heck does this have to do with Venus? Well, it turns out Venus doesn't appear to have the plate tectonics that Earth does, which means that in the normal process of removing heat from a planetary interior needs to have another mechanism. Now, while it's not completely true that Venus lacks plate tectonics, it does appear to implement them in ways not seen before. On Earth, again, the lighter granite that makes up the continents floats on top of an ocean of basaltic magma. This movement of magma carries the continents along and smashes them together or pulls them apart. On Venus, there are no lighter rocks such as granite, and the surface appears to be mostly basalt, without an easy means to move plates over and under other plates. Blocks of granite are generally locked in place. Small movements do occur, and these open up cracks where volcanoes can release the heat and gases. Now, this is a view radar view of Nuwa Compass. Again, I'm hoping I'm pronouncing that correct. The largest block of basalt in the Venus lowlands. You can see the ridges surrounding it that are created when the block kind of moves a little bit around. Because there's no process of creation or destructions of continental plates on Venus, the surface is like a time capsule, being essentially unchanged for hundreds of millions of years. Although it's difficult to be certain, it appears that the surface of Venus is about 700 million years old. So what happened back then? Scientists are still debating whether there was a great resurfacing of the surface, whether that occurred, which would be an upheaval that erased any evidence of the previous Phoenician surface from earlier ages. It's difficult to imagine conditions that would cause such an event to occur, but it would go a long way in explaining what we see today. We see large impact craters, but unlike the moon, the surface hasn't been turned over and over countless times by the bombardment of meteors. We do see large impact craters, which are tens to hundreds of miles across. While the relatively low resolution of the Magellan images makes it impossible to see the smallest craters, there isn't a significant number of impact features below a few miles across. And we should be able to resolve those. There appears to be two reasons for this. First, we believe that the near constant volcanic action is filling in all the smaller craters, leaving only the, obliterating them from view and just leaving the largest ones. But just as importantly, the incredibly thick atmosphere causes all but the largest meteors to burn up before they reach the surface. Another way of thinking about this is like throwing rocks into a stream. A small rock hits the water but quickly slows down as it passes through the viscous water. As a result, it doesn't make much of a disturbance when it hits the bottom. A large rock has enough mass and momentum that it would still be moving pretty quickly, enough that it would hit with a large amount of force when it smacks onto the bottom. Moving on from the surface of Venus, let's turn to another defining characteristic of the planet, its dense atmosphere. There's no earthly analogies to what exists there. Carbon dioxide composes about 96.5% of the atmosphere, with about 3% nitrogen. Trace amounts of other gases, most notably sulfur dioxide, drive the chemistry of the environment. Water exists as well, but in very, very small quantities, as well as hydrogen fluoride, hydrogen chloride, and other gases that are common in volcanic eruptions. The pressure on the surface is immense. 1,350 psi, or about 92 times the pressure here on Earth. That is about the same amount of pressure found 3,000 feet below the surface of the ocean. When you consider that this is about twice the depth of a nuclear submarine can achieve, you can imagine designing a probe that would survive such an environment. Opaque clouds exist in the upper atmosphere, but the lack of water means that they're not the kind of clouds you would find on Earth. Rather, these are clouds of concentrated sulfuric acid. A component of volcanic gases on Earth, Venus, and Jupiter's moon is sulfur dioxide, which, after a series of chemical reactions that we'll discuss in a bit, sulfur dioxide combines with water to make the acid. An interesting effect occurs with the thick layers of clouds. Venus reflects about 75% of the incoming light and heat. That's more than twice than what's reflected by the Earth. This creates an apparent paradox. If reflectivity were the only determinant of a planet's atmosphere, a planet's temperature, Venus would be a hot and steamy place, perhaps a bit warmer than the tropics here on Earth. However, as we learned from as early as the Mariner 2 mission, the planet is very, very hot. Later missions would find that the temperature is nearly 900 degrees. The temperature is due mostly to the immense pressure of the atmosphere at the surface, and also to the significant greenhouse effect of the carbon dioxide that's there. A further surprise is that the temperature of Venus is very near the same on the day side and the night side, and cools only slowly and in small amounts as you go from the equator to the poles. To cap off our summary about how extreme the atmosphere is, it's important to note that near the surface, the atmosphere isn't even a gas anymore, or a liquid, or a solid. It's called a supercritical fluid, and the word fluid here is used loosely. The properties of the carbon dioxide at that temperature and pressure are neither a liquid or a gas, but take on unique characteristics of their own. One important property of supercritical carbon dioxide is that it conducts heat very, very well, and it's one of the main reasons why the day and night sides of the planet are very nearly the same temperature. In the end, to say Venus is hellish really does a great disservice to hell. The inferno that Dante envisioned seems to honestly be a far nicer place. We talk about the immense amount of carbon dioxide in the atmosphere of Venus as if it's some sort of oddity. Of course, that's from our perspective from a modern Earth. Setting aside the human contribution to the carbon dioxide burden in the Earth's atmosphere, we see three planets whose atmosphere appears quite different. Venus is dominated by vast quantities of carbon dioxide. Mars has a thin atmosphere, again, of mostly carbon dioxide. And Earth seems to be the exception with its oxygen-nitrogen atmosphere. At first blush, we might argue that the three planets had completely different evolutions. But again, we're just looking at a single moment in time, and this leads us to very incorrect conclusions. We know from our study of Mars, for instance, that it was a far warmer place billions of years ago. It had a thick atmosphere like that on Earth, and water flowed freely. The ancient volcanoes on Mars gradually cooled off, leaving the planet without a source of gases for its atmosphere. Eventually, a number of factors conspired to cause the atmosphere to leak away, leaving the planet dry and cold. Earth has a more interesting case in planetary evolution. Early Earth, billions of years ago, was intensely volcanic and had a thick atmosphere of carbon dioxide, not unlike Venus. But why did the evolutionary paths of Earth and Venus diverge? The answer is simple: water. As Earth cooled, vast amounts of water were able to condense and form the lakes and rivers and oceans that we have today. Carbon dioxide is very soluble in water, which we know when we open a bottle of soda or champagne. With that abundance of carbon dioxide, forming rocks out of that basic compound into carbonates is quite straightforward. As life began to evolve, organisms incorporated those carbonates into their bodies. They lived, died, and deposited those compounds on the bottoms of the ocean. We see the results of this billion-year process when we see the White Cliffs of Dover in England, or the entire state of Florida, which is made predominantly of the limestone formed by ancient skeletons of sea creatures. If water on Earth never existed, carbon dioxide would never have been withdrawn from the atmosphere, and the carbonates would never have formed, to the extent that we see today. And yes, Earth would quite easily become the hellish twin of Venus today. How do we know this? When we look at the amount of carbonaceous rocks on Earth, we find that the amount of carbon dioxide bound up equals, to a first-order approximation, the amount of carbon dioxide we see on Venus. Pretty amazing, isn't it? On Earth, weather and much of the climate is dominated by the water cycle. We have a vast reservoir of water in the oceans, which evaporate, condense to form clouds, and then return to the surface as rain or snow. Water also takes on solid forms as the temperature gets colder and we have snow and ice. But importantly, water remains just that. It's just the same H2O everywhere, changing only as it transitions between liquid, gas, and solid. On Venus, the atmosphere is dominated less by temperature swings as it is by the chemistry of sulfur and its interaction with carbon dioxide and the little bit of water that exists. High in the upper atmosphere, the intense ultraviolet light from the sun rips molecules of carbon dioxide and water apart, which then combines with sulfur dioxide to make sulfuric acid. As these molecules collect, they form droplets, and when they start falling, they form the sulfuric acid clouds that cover the planet. More and more of the acid combines in larger and larger droplets, which then fall towards the surface in the ultimate form of acid rain. Like the well-known phenomena on Earth of virga, where rain evaporates before reaching the surface, the acid rain evaporates at about 25 miles above the surface of Venus, breaks back down into water and sulfur dioxide, and the cycle keeps repeating itself. The ultraviolet rays at the top of the atmosphere also break apart molecules and eject them from the planet before they even have a chance to recombine. Sulfur dioxide doesn't stay in the atmosphere for long and is split into sulfur and oxygen ions, and so that has to be replenished. Since the only possible source from these gases is from active volcanoes, we have yet again more evidence of a geologically active planet. But sulfur isn't the only element that's a victim of the sun. We have long speculated that long ago, Venus had lots of water, and perhaps even oceans. But if it did, where is it now? As we see on Mars, we know to look for a specific signature of past water that might have been lost to space. Now, water comes in with its hydrogen in two different isotopes. Regular hydrogen, which is just a proton and electron, and deuterium, which is twice as heavy as it has a neutron as well. When a water molecule is split up by the sun into the oxygen and hydrogen, the ordinary hydrogen, the light hydrogen, is more easily accelerated into space and lost forever. The heavier version, deuterium, is not so quickly ejected from Venus and tends to stay in the atmosphere much longer. With this process occurring over billions and billions of years, we would expect that there would be much more deuterium in the atmosphere other than the regular hydrogen. And this is what we see. There is a huge imbalance of hydrogen to deuterium in the atmosphere that not only tells us that Venus had far more water in its distant past, it also gives us a reason why the planet is so arid today. The weather forecast on Venus is always pretty boring. Every day, it's everywhere on the planet, and it's always the same, cloudy and hot. Now, let's turn to the reasons for this rather repetitive forecast. On Earth, water is a primary driver in all aspects of what we call weather. There's an old joke that the recipe for weather is take air, add water, heat, and then stir it up a bit. And that's surprisingly accurate. The temperature differences across our planet comfortably share the same ranges of water as it exists as a liquid, gas, or solid. Earth also rotates at a pretty fast clip, about 1,000 miles an hour at the equator. The rotation of our planet also creates an interesting effect called the Coriolis force, which is not a force at all, but the tendency to set moving parcels of air spinning, just like what we see with this picture of Hurricane Ida. We see the effects of absorbing and releasing huge amounts of heat from the tropical oceans, which are then set spinning by the Coriolis force. We saw the end result of this all too well as Hurricane Ida pummeled the Louisiana coast in late August. Moving to Venus, much of everything what we know about meteorology can be thrown out the window. So, what kind of weather, if you can call it that, exists on Venus? Weather, as we would define it from our experience on Earth, simply doesn't exist on Venus. First, water, or any reasonable substitute for it, doesn't exist in any meaningful amounts on the planet. Even if it did, temperatures and pressures in the lower 20 miles or so of the atmosphere would turn water in any form into superheated steam. As we saw, only at very high altitudes, at least 30 miles above the surface where the environment is almost Earth-like, is it cool enough to allow any condensation of gases into droplets. Of course, these were the sulfuric acid clouds that prevent us from seeing the surface. Next, unlike Earth, Venus rotates very, very slowly. Rather than the 1,000 miles an hour rotational speed of the Earth at the equator, Venus rotates at a lethargic 4 miles an hour. Yeah, you could easily jog faster than the planet rotates. This prevents any kind of Coriolis force from spinning up the air masses, making it impossible for it to form any kind of the storms we see on Earth. We also know that storms, or weather in general, is actually the means for air masses to equalize the temperatures of the Earth. After a series of long, hot, sweltering July days, we know that Mother Nature will send in a blast of cooler air just to balance the temperature differences out. This is certainly not the case at Venus. Since the lower atmosphere is this supercritical fluid and transfers heat so easily, there simply aren't large temperature variations across the planet. Even a tilt of the rotational axis, which creates the different seasons on Earth, doesn't exist on Venus. Only at the poles are the temperature differences meaningful, and even then, it's only perhaps 80 degrees cooler than the rest of the planet. This sets up a textbook model of what are called Hadley cells, which is where the air warms up at the equator, flows directly northward or southward toward the poles, where it sinks to repeat the process. What is unusual is that the upper atmosphere that we see has very, very fast-moving winds, some moving in excess of 200 miles an hour. Of course, this is far faster than the speed that the planet itself rotates at. So, Venus still has a lot, left to teach us. We have spent the last several years digesting the results of all the previous missions to Venus. We still don't have answers to some of the most basic questions that are out there. We notice there are regions in the clouds where ultraviolet light is practically completely absorbed, but we don't have explanations for this. An answer to that question alone might explain some of the very dynamic processes we see in the atmosphere. Maps created 30 years ago by the Magellan spacecraft are at a far lower resolution than even the most basic spacecraft used today. A modern update to the maps is essential if we are to see the details and processes that have occurred since our last visit. And we're in luck. This year, NASA approved 2 new missions to Venus that will significantly expand our knowledge of that world. The primary mission of the first, Veritas, will map the surface with a resolution about 10 times that of Magellan. It'll also study the heat radiating from the surface and the gravity fields of the planet. The second spacecraft, Da Vinci Plus, is studying the atmosphere in far greater detail than before. Like other missions before it, it'll drop a probe into the atmosphere which will report on atmospheric composition. Like the Huygens probe that landed on Saturn's moon Titan, it will take high-resolution photographs during its descent and hopefully after it lands. The Da Vinci orbiter will study the geologic plates of the surface and the origins of the planet and atmosphere. Finally, the European Space Agency has also just announced that its new Envision spacecraft will also orbit Venus, with instruments that will complement the Da Vinci Plus mission. All 3 spacecraft are working towards a 2031 launch date, so stay tuned. So, that's our long talk on the mysteries of Venus and what we've learned over the decades. I really hope you enjoyed it. I know this one was long, and I hope you got a lot out of it. Next month, we're going to be talking about the new missions that NASA has been flying since the last flight of the space shuttle. It's been 10 years since Atlantis flew on its final mission of the program, and it ended a monumental era in human spaceflight. But we haven't been sitting idly by. A new generation of spacecraft designed to fly to the International Space Station has been built with the idea of eliminating our dependence on the Russian Soyuz spacecraft. Orion and the Space Launch System are also being readied for flight, ultimately to the moon. It promises to be a great lecture, and I hope to see you there. Until then, please stay safe and healthy.